So today we're going to focus on conjugate addition reactions, and we've already talked about conjugation a lot. We did this last term, right? Where we said a conjugated system occurs when you have these alternating pi bonds. So is this a S-cis or an S-trans diene? Trans, right? And we said that that has its own unique reactivity, and we said that it's very, very different than a non-conjugated system where you have an sp3 carbon. So we saw in the chapter where we covered conjugate systems or conjugated pi systems that you can do Diels-Alder reaction, you can do halogenation with a 1,2 fashion or a 1,4 fashion. Do you guys remember that? We're going to do a similar set of reactions with ketones and aldehydes that are conjugated. So let's take a look at a conjugated ketone. In this case, it's conjugated, right? We have alternating double single bonds, but one of the double bonds is now a CO double bond. And this is very, very different than a system that would look like that, because in this system, just like in the other one, we've got an sp3 carbon. So this is non-conjugated, where this one's conjugated. Does anybody remember the functional group name for that ketone? It's something unsaturated.
Alpha beta.
Alpha beta. And we said we could make these by first doing alpha halogenation and then doing an E2 reaction, right? So that goes back to the first reaction we talked about in this chapter, but these are pretty easy to make. They're thermodynamically very stable when you form that alkene. However, they do have some unique properties, especially as electrophiles. And let's take a look at why that is the case. So for conjugated ketones or aldehydes, so let's go through and draw all the resonance structures for the simple one that I just showed you guys. So we could do one where we kick up electrons onto that oxygen. It's pretty easy. That gives us a positive charge down on that lower carbon. Then we can go ahead and we can say, all right, this pi bond can hop over. Are there any other major resonance structures? What do you guys think? Sometimes people get really tempted to say, well, why not a resonance structure like that? So for example, is this a valid resonance structure? Yeah, we've got a positive and negative on two adjacent carbons. Those are so minimal, don't even bother drawing those. They're a waste of time. So the top three resonance structures are going to be our major ones. And the interesting thing with these is if we consider the electrophilic positions, we've got two different electrophilic carbons, right? So this carbon's electrophilic and that carbon's electrophilic. So this is pretty similar to the 1,2 versus 1,4 conjugate systems that we saw before. In this case, we start numbering at the oxygen, and we'd say 1, 2, 3, 4. Whoa. The one on the left, where the positive charge is on the carbonyl carbon, if your nucleophile attacks that carbon, it would be 1,2 addition. And if it attacks the carbon on the far side, it would be 1,4. So 1, 2, 3, 4. This would be a 1,2 addition product. And then this one would be a 1,4 addition product. Does that make sense? A lot of this is kind of review. I just call them 1,4 addition products. Yeah, or conjugate addition is adducts. Adducts are typically used for Lewis acid base pairs, not for nucleophilic attacks. Okay, so the question is, well, which position will get attacked and why? And there are some basic trends you've got to understand before you can do these reaction mechanisms. The first is that strong or unstable nucleophiles favor 1,2 addition. Whereas your weaker or stabilized nucleophiles favor 1,4. Sterics play a small role where we'll go through some examples, but typically a stabilized nucleophile is one where it's resonance stabilized, not sterically bulked up. But these trends are key to understanding these reactivities. Typically, you'll see 1,4 addition called conjugate addition, too. So if you ever see it used in the book, conjugate addition is just shorthand for 1,4 addition. All right, so let's take a look at some reactions here. And we'll do a little review. So for the first one, let's show the full mechanism. And we're going to start out with acetaldehyde, sodium hydroxide, and heat. Come on, pen. So I want you guys to help me determine what the overall product would be with sodium hydroxide and heat. And then we'll go on from there. What sort of reaction do you guys think this will be? So first step, you'll form your enolate, right? And then what will happen after you make your enolate? Yeah, it'll attack another molecule of unreacted starting material. What's this reaction called? Aldol. That's when an enol or an enolate attacks another equivalent of aldehyde or ketone. Okay, so at this point, we're almost there. What will happen next? Got water around. That's our conjugate acid. We're going to reprotonate the alkoxide. giving us our beta hydroxyaldehyde. Plus another equivalent of hydroxide. Now what? I assume there's heat, remember?
Yeah, we use protein.
Protonate what?
The alpha carbon.
So we're under basic conditions. We don't have any protons to
You
donate.
can deprotonate the alpha proton.
Yeah, we could deprotonate the alpha proton. And then what will happen when we do that?
It'll do it fine. It'll kick off the hydroxide.
Kick off the hydroxide, right? This is one of the weird examples where we see hydroxide acting as a leaving group. And voila, we've made our alpha beta unsaturated ketone. So you can make these alpha beta unsaturated ketones using aldol condensation, or you can do alpha halogenation followed by an E2. Either one is very common. Okay, so now that we've got this, let's consider a few reactions. Option 1 is what will happen if we treat this with methyl lithium, which is a strong nucleophile, followed by an acid workup. And then let's consider an alternate reaction where we use a lithium dialkyl cuprate, a Gilman reagent, and again follow it with an acid workup. So with methyl lithium, which carbon do you think is going to be attacked? The 1,2, so the carbonyl carbon. Okay, so if we consider this reaction, we would end up with our 1,2 addition. Does that make sense? And then with the other one, we're going to attack the 1,4 position. So that's the 2, 3, and then over here we'd have our 4. And that would be our addition product. So we do have to keep track of the strength of our nucleophile. This is 1,4 addition or conjugate addition. Since this is a weak or weaker nucleophile. Over here we've got a really strong nucleophile, which favors the 1,2 addition. Does that make sense? So where do you think a Grignard would fall? Do you think a Grignard would favor 1,2 or 1,4? It would favor 1,2 more than 1,4. However, you might observe a little bit of a mixture of both 1,2 and 1,4. Typically, if you really, really want to favor the attack at that 1,4 position, you've got to use an incredibly stabilized nucleophile, meaning the nucleophile has to be very weak. So let's go through and do the mechanism super quick. It's very straightforward. We already know how to do the 1,2 addition one. So let's say we've got this aldehyde. It's alpha beta unsaturated. And we've got a nucleophile. And it's important to remember that this must be weak. Must be stable or weak. And in this situation, all that's going to happen is it's going to attack this carbon. This pi bond can hop over, and it can kick up electrons onto the oxygen. Now we've got our nucleophile attacked. And then in the next step, we said we were going to do an acid clench. So all that's going to happen now is this will clamp down, and then this pi bond will steal a proton from hydronium. And your nucleophile will get attached in that 1,4 position. You can also do this with other resonance structures too. So occasionally what I see students do is they say, you know, we can draw a resonance structure where that electrophilic carbon, contains a positive charge and this oxygen's negative. Is it okay to have the nucleophile attack this way? Yeah, the answer still gives you the same intermediate. So either one, you can draw it either way. And then same thing here, where people say, well, this arrow pushing scheme looks a little bit different and I'm kind of uncomfortable with it. What about this resonance structure? Is it okay to show this negative charge deprotonating or stealing a proton? Yeah, it still gives you the exact same product. So you're welcome to use the resonance structures. You don't have to draw out all the resonance structures if you don't want to, but if it helps, definitely do it. All right. Does that make sense in terms of the basics for conjugate addition?
So since resonance isn't really full on charges, it's kind of just showing the nature of the bonds. It's basically just showing the same thing. It's just, I mean, not just that it's getting the same product, but it's showing that that side is more positive and that side's more negative.
Exactly. Yeah, with resonance structures, occasionally students get really hung up on them, whether they're like, well, which one's correct? Well, they're both correct, right? They're hybrids of one another, so you can draw either one. I'm fine with it. All right, so let's take a look at Michael's reaction. A Michael addition. And this is a very special reaction, which is why I named it after Michael. This is a conjugate addition using a resonance stabilized carbanion as a nucleophile. So let's take a look at an example of the Michael reaction. And we're going to take a diketone, specifically a 1,3 diketone, and we're going to first treat this with sodium hydroxide. Which alpha proton do you think is most acidic?
One between.
Yeah, the one in between. Okay, so the first step is to form our enolate. Yeah. You're saying if you had a double bond to a nitrogen, like an imine? We'll actually talk about a variant of that. So there's something called an enamine synthesis, but we'll get there in a little bit. Yeah. So right now we've got this enolate, and this enolate is incredibly stable. Which means it's a weak nucleophile. Okay, so now that we've done that, we can now treat this with a alpha beta unsaturated ketone or a conjugated ketone, whichever terminology you want to use. And we just said that anytime you have a weak nucleophile, it's going to favor 1,4 addition or conjugate addition. So we're going to attack here, kick electrons over, and all the way up to that oxygen. And then in the last step, all we're going to do is treat this with acid. This can clamp down. This can steal a proton back. And we formed a new carbon-carbon bond. So this is a classic Michael addition reaction. In this case, you may hear some different terminology used. This is commonly referred to as our Michael donor. And this would be our Michael acceptor. Really, your Michael donor is always going to be the thing acting as a nucleophile, and your Michael acceptor is going to be your electrophile because it's accepting the electrons from the donor. So let's take a look at some common Michael donors. We just said that resonance stabilized enolates are good Michael donors, but there's other ones. So you could have an enolate that's resonance stabilized. So something like this could be a good Michael donor. You could do the same thing with esters, where again that's doubly resonance stabilized. Or you can do a combo one. Half ester, half ketone. Or you can have this one. Why is that so special?
Because you kick up a little bit of nitrogen.
Yeah, you could kick the electrons over to the nitrogen too. We said that nitriles behave a lot like carboxylic acid derivatives. So that is also resonance stabilized. Same thing with this one. So if you have a nitro group, these protons are unusually acidic because that nitro group's electron withdrawing, and, oops, I'm forgetting a positive charge. Oh, thank you. I put it in the wrong spot. So that set of alpha protons where the green arrow is pointing, they're unusually acidic because that nitro group's really electron withdrawing and it's resonance stabilized. So in this case, it's only resonance stabilized to the nitro group, but the nitro group's so strong that it's a really weak nucleophile and it's a good Michael donor. The other one that we saw are the lithium dialkyl cuprates. And these are stable not due to resonance, but more due to the unique fact that they're bonded to copper. So these are commonly used for conjugate addition reactions.
I thought you said in order to do Michael addition, have you resonance stabilized carbon.
Yeah, this one's kind of the oddball that doesn't fit the rules, but really any weak nucleophile is considered a Michael donor. Yep.
For making a Michael donor, do they all work okay with sodium hydroxide? Do you say
It depends. So for example, with esters, you wouldn't want to use sodium hydroxide because that would saponify your esters. So commonly you'll use LDA, a non-nucleophilic base that's really, really strong that can abstract a beta proton but won't do any nucleophilic attacks. So LDA is very common for enolate chemistry. Yeah, exactly.
You could do like an opposite apple.
You could. It depends on the situation. So for example, with these esters, you could use sodium ethoxide. That would be fine. Okay, so let's take a look at a practice problem. Okay, so step 1, I'll treat this with LDA. Step 2, I'm going to treat it with an alpha-beta unsaturated aldehyde. And step 3, we'll do our acid workup. What product or products do you think we'll get out? I'll give you guys a minute to work on this and then check with your neighbor. So when we treat this with LDA, we're going to make it an enolate, right? Not an enol. Is that a Michael donor? Why not?
It's not resonance stable. Well, it's not.
It's really strong.
Yeah, it's a strong nucleophile. It is resonance stabilized, but not between two carbonyls, which means that this is a relatively strong nucleophile. Will that favor 1,2 or 1,4? 1,2. So let's determine the product that we would get for 1,2 addition. So this would be our 1,2 addition. This would be our major product. You might observe a little bit of your conjugate addition, however, it's going to be your minor product. So the question is, well, what if we want the 1,4 addition product? What if we don't want the 1,2 addition product? What can we do? Well, we've got to use some chemical trickery. I'll show you guys the workaround. This is called the Stork Enamine Synthesis. So with the Stork Enamine Synthesis, the first thing you do is you make an enamine, hence the name. So let's just pick a generic amine. Should it be primary or secondary? Secondary. So this should be HNR2 and H+. And we'll drive off water during this reaction. And voila, we've got our enamine. Enamines are special because they do have this resonance structure where this lone pair can hop over and dump electron density onto the adjacent carbon. However, that's a really minor contributor in its resonance form, right? Whoops, I forgot the positive up here. Typically, we want to draw resonance structures that are uncharged, which makes this a super weak nucleophile. Okay, at this point, we can then treat this with our aldehyde from the previous reaction, and we know that because this is a super weak nucleophile, that this carbon will favor 1,4 addition, kick up electrons all the way to the oxygen. And then in the last step, we're going to treat this with acid. What will happen when we treat the iminium ion with acid, what will it convert back into? Back into a ketone, right? So we said in the aldehyde and ketone chapter that those reactions are reversible depending on how much water is around. If you flood this with water and acid, you can convert it right back to your carbonyl. And then what happens with this portion over here? Yeah, it'll turn it back into the aldehyde, right? So in this case, we'll do some proton transfers. And you can end up getting the 1,4 conjugate addition product that you want without any of the 1,2 byproduct that you didn't want. Yeah, so the enamine workaround is very common. It's very popular. It's a green reaction. It's pretty easy to accomplish. And it allows you to really use a wide variety of enolates as your nucleophile, right? And we're using enolates in a loose term here because it's not your classic enolate. All right. You guys want to try some practice problems?
Yes.
All right. I'm not sure if we'll have time to get to the next reaction. So propose a synthesis. So we're going to start out, what would that be, 3-pentanone? And our goal is to make this compound. And you can use any reagents that you want, but you have to start with 3-pentanone. All right, let's try to work on this as a class. I'm worried we're going to run out of time. So looking at this and trying to work backwards, we're trying to add in this group, correct? No other carbons are being attached. So the first thing I would do is I would treat this with LDA, or would I do an enamine? Oh, it's tricky, right? Do we want to make a super strong nucleophile or a weak nucleophile, and why? Weak nucleophile. If we look at it, we don't want to attack this carbonyl. We want to attack the 1,4 position, right? So what's a way of making a weak nucleophile? The thing we just learned. So H+, catalytic acid. We typically control this pretty carefully with pH or buffer systems. And we drive off water. Okay. Now we've got our enamine. Okay, and then we've got to determine the reagent. So we know in blue that at this position, right here between the alpha and beta carbon, there must have been some sort of double bond. So we must have had an alpha beta unsaturated ketone. And in this next step, we're going to clamp down. This is going to attack, kick over, and kick up. And now we've got our imine and we've got our enolate. What's the next step?
We do it all with acid water.
Yeah, just acid and water for the next step. So to get to our final product, all we need is hydronium, and we can get to our final product. If you remember, this will convert our iminium ion back to the ketone, and it will convert this enolate portion right back to the ketone as well. I kind of spun the product around, but it's the exact same product, if that makes sense. All right, I think that's where we're going to leave it today. Bring your pod in tomorrow. We're going to work on that in class, and it will be due the following Monday. So you guys can work on it in class tomorrow. Don't worry about it over the night.